Okay, in this video what I want to accomplish is to teach the viewer how to determine whether or not a chemical equation is an oxidation-reduction reaction or not. Oftentimes the acronym for these reactions is called redox, and I'll probably be using that term along with oxidation and reduction interchangeably. Now, as an example, I have we're going to look at this equation here, which is the general class of reaction is called a synthesis reaction because we're combining two reactants and we form a single product. This is also a combustion reaction because the reactant, which is sulfur dioxide, is being combusted with oxygen to produce a new molecule, sulfur trioxide. So the question is, when we look at this reaction or this equation that represents the chemical reaction of sulfur dioxide with oxygen, how do we tell that this is an oxidation-reduction reaction? All right. Now, the first thing is that to be clear about what these reactions are, a redox reaction involves the transfer of electrons. The transfer of electrons. All right. So, in other words, in the reaction between the SO2 and the oxygen, somehow in that process, electrons need to be transferred from one entity or one substance to the other in order to produce the SO3. And so what we need is a method that will allow us to figure this out. Now, what we're going to do in order to figure that out is establish another concept which is called oxidation number. So I'm going to define that over here, oxidation number. Oxidation number. Now, oxidation number is either the formal charge on an element or a theoretical charge. A theoretical charge on an atom based on electronegativity difference. Now, I'm going to abbreviate electronegativity this way. Difference between the bonding atoms. Between bonding atoms. All right. So in this video, there's a couple of things that that the viewer is going to be responsible for, because I can't literally fit everything in to the short series the way I want to do this. The first thing is that you need to understand how electronegativity works. So you need to review those definitions. This is a periodic trend, and maybe what I'll do is just put the abbreviation down here. And in terms of the periodic trend, the electronegativity increases as we go left to right across the table, and it decreases down any group. All right. Now, electronegativity has to do with the attraction that an atom has for electrons when it's in a bond with something else. Then the other basic knowledge that you're going to need is shown here on the lower left part of my screen. In terms of formal charges, you need to remember or have a solid understanding that group 1A elements ionize to form +1 charges when they react with a nonmetal. Group 2As will ionize. Whoops, I see I made a mistake in here. Sorry, let me just fix that really quick. That was supposed to be magnesium. group 2A elements ionized to form plus 2 charges. And then with oxidation numbers, we're going to minimize what we know about fixed charges on the right side of the table. So only oxygen is going to be have a fixed charge of -2. In most of the compounds it's going to be bonded to. And then our 7A's, in most of the compounds that they're bonded to, are going to be -1. And then the other thing is we're going to establish a rule. We're going to say that the oxidation number, or the formal charge that we're going to place on an element in its natural form, is going to be 0. And I've listed many of those here so that we can refer back to these as we go through this process. Alright, so when we look at an equation like this, the SO2 reacting with the oxygen to produce SO3, we need a method that allows us to look at each of the components of this reaction and answer the question, have electrons been transferred from at least one of these elements to something else in this reaction? If the answer is yes, then we know that this reaction is a redox. If the answer is no, then this reaction is not a redox, it's something else. Alright, so let's see how we're going to work this out. The first thing is, we've got oxygen in the reaction, elemental oxygen, and we see that for an element in its natural form, its oxidation number is 0. So I'm going to go ahead and write that in. We have that established for this. Now, the other issue then is everything else that's in this reaction is tied up in a molecule. And that's the issue. We need to figure out what the oxidation number is on the oxygen and what the oxidation number is on the sulfur. Now, for the oxygen, almost any time oxygen, there are some exceptions. We're not going to worry about that in this video though. So most of the time when oxygen is in a compound, its oxidation number or charge is going to be -2. Now that leaves us to figure out the sulfur, and quite frankly the sulfur, since it doesn't appear down here in our little list, is an unknown. So how are we going to figure this out? Well, the first thing is you got to remember that SO2 is a neutral compound. That means the sum total of any charges in this need to be 0. So we're going to set up a little equation for us to solve for the sulfur. And since the net charges of everything in here has to be 0, we're going to set our little equation equal to 0. And our unknown is going to be the sulfur. And that leaves us with the oxygen. But like I said, we already know that the oxygen is going to be -2. We need to figure out the net charge on it though. And since there are 2 oxygens in the molecule, we need to multiply the individual charge on the oxygen, which is -2, by the number of times that element appears here. So the total net on the oxygen is going to be -4. So now we can solve for the sulfur by simply subtracting the net charge of the oxygen from the sulfur. And we solve for the S. And that means the oxidation number on the S in SO2 is +4. So I'm going to write that up here. We got +4 on the S. We've got -2 on the oxygen in the SO2. We've already established that the O2 is 0. And that just leaves us to figure out the SO3. So I'm going to write that down here. And we're going to use the same rationale that we used to solve the SO2 to solve for the SO3. Alright, again, the oxygen in here is -2. And there are 3 of them, which means that the total net oxidation number on the oxygens, the total charge is going to be -6. We set up a little equation. Set the whole thing equal to 0 because this particle has no charge on it in total. Alright, we're going to solve for the sulfur. The total oxygen is -6. So the sulfur in this case is going to be +6. All right, now, in order to answer the question, is this a redox equation or not? Is this a redox reaction? Is the combustion of sulfur dioxide with oxygen to produce sulfur trioxide a redox reaction, oxidation reduction? So we can see, first, if we focus on the sulfurs, that we go from +4 on the reactant side to +6 on the product side. The only way that can happen is if the electron content of the sulfur has changed. And the only way to go from +4 to +6 will have been to have lost electrons. So I'm going to write that down. This lost electrons going from here to there. So we say that the SO2 was actually oxidized. So we have actually answered this question. This is definitely redox. So yes, redox. Yes, redox. Because we've shown a change in at least one of the components. Now, let's not ignore the oxygen. We see that it goes from a 0 oxidation number to -2. All right? So the oxygen here has also undergone a change. It has gained electrons. So O2, oxygen, gained electrons from this point to this point. So we say that the oxygen is reduced. So in summarizing, what we learned to do here was to establish an oxidation number or a formal charge on each of the elements that are involved in the total components of the reaction. Then we looked for a change. You only need to find one change in order to establish whether or not a reaction is redox or not. We found the change in the sulfur, and we also have one in the oxygen. Therefore, this equation, the way it's written, this combustion reaction, is in fact a redox reaction. And we were able to establish that one of the components, the SO2, was oxidized, and that one of the components, the oxygen, was reduced. So the oxygen gained electrons, and the SO2 lost electrons.